All right, today we're going to talk about an idea that feels like it's been pulled straight out of a sci-fi novel, but is actually grounded in some really fascinating and kind of weird physics. We're talking about gravitubes. So let's just jump right in with a wild question. What if you could get from New York to Sydney in about the time it takes to watch an episode of your favorite show? I mean, that sounds completely impossible, right? Well, maybe not. So how would this even work? Well, the secret is a concept that's as simple as it is, absolutely insane. You just build a perfectly straight, frictionless tunnel that goes right through the planet. That is the heart of the gravitube. So, to put a name on it, what exactly is a gravitube? Well, it's a theoretical tunnel where the planet itself does all the work. The whole point is to have super fast travel with almost zero energy cost, because you're literally just letting gravity be your engine. And the principle behind it is so elegant, it's kind of beautiful. You just step into a capsule on one end of the tunnel, and you fall. That's it. Gravity pulls you down, you build up a ton of speed, and that momentum is what carries you all the way up to the other side. Okay, but wait a second. This brings up a really important question. Our entire understanding of gravity is based on being on top of the Earth. What happens when you're actually tunneling through it? This is where the physics gets a little strange, and honestly, really cool. Now, this is where your intuition might completely fail you. You'd think that the deeper you go, the stronger gravity gets, but it's the exact opposite. As you fall, all the mass of the Earth that's above you starts pulling you back up, canceling out some of the force from below. It actually decreases in a straight line until, at the very center of the Earth, you'd be totally weightless. And this behavior, a force pulling you toward the middle that gets weaker the closer you get, is described by a classic physics principle called Hooke's law. But you don't need a physics degree to get it. The best way to think about it is a giant spring. The more you stretch it, the harder it pulls you back. So here's the key idea you need to hold on to. For our trip inside this gravitube, the Earth's entire gravitational field is basically acting like one enormous, perfect spring. You're just an object attached to it, bouncing back and forth. And this is where we get to the big, mind-bending reveal. So let's picture two different trips. One is the longest possible journey you could take, straight through the center of the Earth. And the other is a much shorter trip, a little shortcut that just cuts across a chord of the planet. Now, common sense is screaming at you, right? The shorter tunnel has to be a faster trip. It's less distance to cover. But remember that whole spring analogy? Does how far you stretch a spring change the timing of its bounce? And here it is, the astonishing answer. It doesn't matter. It doesn't matter if you're going 10,000 miles straight through the core or 1,000 miles just under the crust. The trip takes 42.25 minutes, every single time. How is that even possible? Well, it turns out the travel time has nothing to do with the distance you travel. It's all determined by the planet's average density. See, on the longer trip through the center, gravity is stronger, so you accelerate way faster. On the shorter trip, the pull is weaker, so you move slower. And the magic is, the higher speed on the long trip perfectly cancels out the slower speed on the short trip. The timing is always the same. Just let that sink in for a second. New York to London, about 42 minutes. Paris to Tokyo, yep, 42 minutes. A gravitube just to get across town, you guessed it, 42 minutes. And this physics works on any rocky planet, what they call a stony planet. If you tried this on a gas giant, the trip would be a little longer, maybe an hour or two, but still incredibly consistent. I mean, this just sounds too good to be true, doesn't it? A global transport system with one universal commute time, and it's all powered by gravity itself. It seems like the perfect solution. So you gotta ask, what's the catch? And yeah, of course, the reality is a whole lot messier. The dream of energy-free travel runs smack into things like friction and air resistance, which you'd have to figure out how to eliminate. Not to mention the engineering challenges are, well, they're astronomical. We're talking about unbelievable construction costs and building tunnels that can survive the insane heat and pressure deep inside the Earth. You know, for most of history, when energy was cheap, this was all just a fun thought experiment. But the source material brings up a really important point. As we move into what it calls an expensive energy economy, do these huge physics-based ideas start moving out of science fiction and into the realm of necessity? I love this.
The source even tosses in this amazing quote, supposedly from a Starfleet engineering manual, that just perfectly sums the whole thing up. It's a fun little nod to the sci-fi feel of it all, but it really drives home the physics behind it.
So that leaves us with the big question, doesn't it? Are gravitubes just going to stay a cool fantasy, a fun problem for physics classes, or are we actually looking at a blueprint for a future that could totally redefine how we connect our world? For now, I guess we'll just have to wait and see. Thanks for joining me.